Okay, today we're going to do a demonstration about angular momentum, and specifically the conservation of angular momentum. And this will help us explain why when a star forms, a rotating disk of material forms around it almost all the time, and how planets can then form out of that disk. So, Caitlin is here to demonstrate conservation of angular momentum. Let's remind you what you learned in the lecture, that L is angular momentum, and it's equal to the mass of a blob of material times its rotational velocity times R, the distance between the rotational axis and a mass. So maybe this is a cloud that's just collapsing to form a star at the center. And we have a blob of mass here and a blob of mass there. Okay? So here's our rotational axis. Its cloud is very slowly spinning around. Where does it get that spin? Usually from a passing cloud of gas. Gives it a little initial spin. When this mass wants to collapse due to gravity and go toward the center, this mass has a lot of angular momentum because the distance here, R, perpendicular distance between the blob of material and the rotational axis there. It's key that this distance, R here, is the perpendicular distance. Okay? This distance here, if this mass blob is right there on the rotational axis, its distance is 0. R is 0 there. So this guy here will have, with this R being 0, will have no angular momentum. It can fall right on top of the collapsing star with no problem. However, this object here, if it wants to go inward and decrease its radius due to gravity, what happens is as R goes down here, V goes up, the velocity, the rotational velocity has to go up. That's called the conservation of angular momentum. So as this mass collapses onto the star, it's going to pick up a lot of rotation. Okay? Now this gas can quickly fall down on the star because it has no angular momentum. It always has no angular momentum if it keeps that radius. All right, so Caitlin's going to show us what happens when we change our angular momentum. We change the distribution of mass. We'll visibly see how something can rotate faster. Ice skaters do this all the time. Okay, so Caitlin, hold out your arms. I'll keep you from rotating. Hold out your arms a second. So we're going to increase the effect by having Caitlin hold some weights here and some mass. And so I'm going to give her an initial spin. One more time. All right, Caitlin, bring in your mass. So you can see the rotation speeds up. Okay, bring out your mass again. And she slows down her rotation. So that's the conservation of angular momentum, and an ice skater will do that in order to have a really nice fast spin. Okay, so now let's illustrate. So the material that collapses from the equatorial regions, the region out here, that will form the highly rotating disk around a forming star. But the mass on the poles, both at the South Pole and the North Pole, because its radius is so small there, we'll be able to collapse right down on the star. And that's why in the polar regions, the mass just comes crashing down on the star. And we end up forming a protostar in the middle with a rotating disk around it. So Caitlin's going to show us if she holds her mass, one of her weights straight up, she can bring that mass up and down without changing her rotational velocity at all. So give it a try. So bring your hand down. We see you don't change your velocity, bring it up, still no change in velocity. But if you move it out, that will slow down your rotation. Okay. So that's conservation of angular momentum, and it's a really key concept for understanding why any star that's forming from a collapsing gas cloud got to have a rotating disk of material around it. And it's inside that rotating disk of material where then planets can form out of the lumpiest, densest bits of the accretion disk.